CLion, a cross-platform IDE for C and C++. Download now.
So hi, I'm Denis. I'm a performance engineer at Meta. And my talk is titled SIMD Substring in a String. Okay. So about this talk, like if you want to, this is the link to the slides, but honestly, I just posted to Discord. And again, please find your way to Discord because I'm going to ask you questions and then you'll need to type things. It's tinyurl.com/dys-2025. Let's agree that we are only talking about n times m algorithms, right? We're not doing any tables today. We are just doing n times m. Okay. We're gonna start with just an interview problem. Right. So imagine that somebody comes into you and you need to give them a problem of like finding substring in a string during job interview. So what you would like them to write? We're going to look at that and we're going to understand the performance implications of that code. Then we're going to look at C++ standards and what it has to offer as far as substrings in strings and how that performs compared to our interview problem solution. And finally, only after all of that, we're going to look into some SIMD code. All right. So interview problem, like imagine you do an interview with somebody and you give them, please write a substring in a string. What you would expect them to write, like just some keywords. Okay, let's try with the next one. So I would expect them to write one of two things. So one thing I would expect them to write is they can maybe write a nested loop, right? And the other thing they can also reasonably write is find plus equal. You find the first character, and then you compare for equality. So, okay. This is my implementation of that code. Like, I don't expect you to understand it, but just kind of like it is here. So here's find, and it's equal. That's the first method, right, in the loop. In the second method, I have an outer loop, and inside of this outer loop, I do an inner loop. Right, I put it as an inner loop inside the lambda, but it doesn't change anything. It's still the inner loop. Okay, so looking at these examples, do you have any opinions about the performance of the things? Like, do you think maybe they're the same? Do you think that the first one is better? Do you think that the second one is better? Any considerations at all? So in this case, on the left, right, what we have to do all the time, right? So imagine that the first character is quite often. And then what happens is then we call equal fairly often. And for example, for every call to equal, we have to do bounds check because we don't know if the string is empty or not, right? And here we don't have that bounds check. So it's really nicely flowing. On the other hand, these two functions come from the standard library, and maybe standard library did something smart here. And then if they did something smart, then the first one would be better, assuming the first character is rare enough. And in fact, the standard library did something smart. So this is that code compiled with libc++. And if we look here, we will see that there is a call to memchar and a call to bcmp. bcmp is almost like memcmp. So this is a libc function that is very fast. And therefore, my assumption would be like this, right? If the first character is rare, then the find plus equal should be better. The way I'm going to measure it is I'm going to search for 22, like so 22, in a bunch of ones. So the first character is not like rare, it's just never even encountered, right? The second thing is I'm saying if the first character is often, so if we often go to that equal part, that the second implementation should be better. And the way I'm going to measure it is I'm just going to, every character is the first character. I'm searching for 12. And finally, the last considerations that we're not going to talk about much is very long needles, right? Same as memchar will be optimized by libc. bcmp, like memcmp function to compare strings, will also be super optimal. And so it will be better for like really long needles if the comparison fails far enough. basically we don't care, but that's another thing. Okay, so let's have a look at the numbers. Here I have my find to equal. This is my two loops. I have a 45 times difference, more than that, between them. Here is the other way around, but this is a benchmark where the first character is all the time, and the benchmark goes the other way. So the two loops is about 5 times faster than find plus equal. This is kind of a problem, right? So both of these are not acceptable. Of course, this performance is amazing. I would like it, but not at the cost of false positives being this expensive. At least not in general cases seems unacceptable. All right. So let's have a look at what we can do. And so how does C++ standard solution for substring and a string perform against these examples? Anybody knows how you can find substring and a string in standard C++? All right. So there is a method on string and string view, first of all. Right. There is a standard library algorithm called standard search. It is a, iterator solution. There is a C function called strstr, right? There is also regex and searchers. Like we're not going to searchers, I mean Boyer-Moore searcher, Knut-Morris-Pratt searchers, that kind of stuff. We're not going to talk about those. We're not going to talk about regex. I just felt like including them. Let's have a look at the numbers. Okay. So this is all right. This is our two loops solution. This is standard search. So standard search is in fact like just better than my two loop solution in every way possible. So we're just going to drop my two loop solution and forget that it ever existed. Now this is a two loop solution search. This is search find equal, like the find followed by equal, and this is string view find. String view find and search find equal are the same because this is exactly the same code. This is what they do, right? They search for the first character using whatever memchar, and then they compare using a libc function as well. So this is exactly the same code. And this is strstr. Strstr is about 3 times slower than string view find, but it is still substantially better than standard search, which is the standard search is it's pretty close to my two loop solution. It's just better. Now let's look the other way around. So when we have false positive, so string view find and search find equals are equally very bad. And so we're going to remove our two loop solutions that it was worse. And this is standard search. Standard search is about 8. I'm going to 7, 8 times better than string view find if every time the first character. And strstr actually, so let me remove this. strstr stays the same. It was 30 nanoseconds where the first character was never encountered. It stayed 30 nanoseconds when every character is the first character. What's happening? Well, stepping a bit forward, actually the secret is they check first 2 characters. Because this is really going to be the worst case for strstr, where I'm doing first 2 characters match all the time. But even still, the first case for strstr is only 3 times slower than standard search. It's not whatever it was, 7 times slower. So at this point, I'm going to say strstr is pretty good. We're going to try to make performance match strstr. This is our goal. We like strstr. Now we can talk about SIMD. Unless somebody, okay, if you have any questions, you can type them and I will go back and answer. That's okay. So jumping into substring in a string using SIMD will be too much. So we're going to start with memcmp. We're going to look at memcmp first because I really like it. And then we're going to look, after memcmp, we're going to look at memchar. And finally, after memchar, only after that, we're going to look at search. So look at the substring in a string. Okay. So standard memcmp. Right. So two arrays, and two arrays, you compare them less, equal, or greater, and you return a negative number if it is less, 0 if they're equal, and a positive number if they're greater. I promised I'm not going to ask you. Okay. So in C++ standards, there are kind of two algorithms you can use to implement this. Just like, okay, imagine we have to write this now, right? And we just have a C++ compiler with shipping libc implement by us. We can use two things. So two algorithms. We can use mismatch to find the position of the elements where they're not equal. Or we can use this fancy algorithm from C++20 called lexicographical compare freeway. But in reality, lexicographical compare freeway is, of course, probably just calling mismatch. Mismatch is the main algorithm. And if you look at the code of mismatch, just from like, let's say, CPP reference, this is kind of what it does. Like, so it goes element by element and compares two arrays for equality. However, even in standard C++, we can do better than this. We don't need to go character by character, right? For characters, we can instead, for example, use int64s, right? So we can go by int64s, and yeah, it's a bit awkward. Like you get like the pointers might not be aligned, so you need to do like unaligned loads. You have to do something with the tail, but generally speaking, you could implement it. By the way, if you need to do the unaligned loads in C++, you use memcpi. So you take an int64 and you memcpi to it. I said we have to do with the tail. So how can we compare 16 bytes? In standard C++, nothing fancy. So we could compare two int64s. Right? We just take two int64s, and like, so two comparisons, if both equal, then the whole thing equal, right? Same as we just discussed. So, okay, I'm going to try this one. Do you know how to compare 15 bytes? Like 16 bytes, we just take two int64s. How can we compare 15 bytes? Okay. So we could, same as we did two int64s, we actually can still use two int64s. We just need to overlap them. So if we overlap two int64s, we just compare this one byte twice, but it's okay. Like because we compare the one byte twice, nothing changes. And in fact, this works all the way down to like 7 bytes. If you go down to 7 bytes, like you cannot load 8 bytes already. This might seem a bit esoteric, but actually, if you look inside the memcp or like memcpi, something like that, this is kind of the code they will be doing there. All right. We'll come back to that later. Now, you might think that the compiler, if this was beneficial, compiler would do it for you, but actually doesn't. So this is whatever I copied from CPP reference. And this is whatever I wrote within 64s. The difference here is 8 times. Okay. This is standard mismatch. So the algorithm we said we can use to implement memcp. The standard mismatch is another twice as fast. Right? And finally, this is standard memcp. Standard memcp is another twice as fast than standard mismatch. This performance of standard mismatch is very new. Like it was added last year, and like literally last time I showed this memcp comparison benchmark, mismatch was not as good. Mismatch was here. As this is very recent work done by Nicholas Clauser. So we really appreciate that work. About this difference between standard memcp and standard mismatch, I will be talking substantially later, but I will explain it. Okay, so how do they do it? Well, generally speaking, right, the idea behind doing mismatch as a memcmp is not that different from what we did within 64s. It is just we are not going to use in64. So in64s are integers. They're designed to be integers and they're really good at them, but they're not designed to be a bunch of bytes. The special registers that are. Those registers that are designed to be a bunch of things are called SIMD registers, right? On my computer, on the measurements I showed you, I use 32-byte registers, and this is 32-byte registers, right? This is why this difference is about 32 times, because they're comparing 32 bytes at a time. So there are many different ways to access SIMD registers. I'm going to use Eve library. So Eve library is on GitHub. It's maintained by Joël Falcou, Jean-Thierry Lapreste, Alexis Anu, and me. However, we don't care here about the libraries. This is not talk about the library. If you want to talk about the library, it's called SIMD in C++20 Eve of a new era. In the library, we have algorithms, and one of the algorithms we have is called mismatch. I'm trying to click. Why is it visible? I thought it should go away. Thank you. All right. Well, let's see how if mismatch behaves. So this is if mismatch. This is memcmp. They are almost the same. They're a little bit different. I maybe know how to fix it, but I didn't. So this is standard mismatch, substantially slower than evalgo mismatch, and this is ints. On ARM, however, this is a difference. This is the same measurements, but taken on Apple M2. And on Apple M2, Eve algorithm is actually beating standard mismatch by about a factor of 2. Not quite. And you can see here that standard mismatch on Apple is very bad. As I mentioned, the performance optimizations for standard mismatch are super recent. So Apple doesn't ship them yet. All right. I will explain this differently. So I mentioned there are some special registers that are wider registers designed to be a bunch of bytes. Those registers called SIMD registers. However, you need to understand that this is like extensions. Your standard C++ doesn't have them because they're platform specific. Right? They're very, very platform specific. Like on x86, there's a bunch of different variations. We were targeting this one specifically, but there's like all of these ones. Right? On Apple, we're targeting this, right? But there's again like a bunch of different variants. And it's important to know which one you're targeting. And it's important to compile to the correct one. So I'm not going to explain you how, but I'm just going to show you. This is if compiled with just default all free, and this is compiled correctly. And the difference here is 2x, because the default one can only use this very weak extraction set. So mismatch seems like what we want. Let's have a look inside, right? Unfortunately, well, it's a library, it's a ranges library, and we worked really hard to make it composable. I want to think it had, and so inside mismatch is just calling findIf plus zip. That's it, which is great for the library. It just doesn't explain very much how it works. So let's have a look how we could implement. Let's look at find. So instead of looking at mismatch, let's look at find, and let's implement find. Okay. So imagine like this. So you write your loop, and you go through, and you finally you want to go through like let's say by 32 bytes, because on my machine the register 32 bytes, and you want to check those 32 bytes for a needle, right? This would be the function. I take a pointer, right? This is where I'm going to take the 32 bytes from, and this is the needle I'm going to compare against. So okay, step one, I need to declare a register. Right. So what this does is this declares on my this selects the correct register for my for the platform. On my machine, this is going to be 32 bytes. Right. Then what I do is I load that register. So I go load from the pointer. This will load me 32 bytes. In the example, is just 4, but generally speaking, that's 32. Then what I do is I compare the loaded bytes against the needle, right? And when you compare this like large register against the needle, what it does, instead of returning you just one Boolean value, like in normal comparison, it returns you, in this case, 32 Boolean values. So this logical byte is going to be special register containing 32 Boolean values, right? In the example, let's say my needle was 1, contents of my register was 0, 1, 2, 3, then the test will be false, true, false, false. Then I will call another special function called first true, right? So what this does, it finds the position of the first true element in the bunch of logical. So I have like 32 booleans. It will give me the index of the first true. Right? If there isn't one, it will return me a null opt. Right? And I say, oh, okay. If there is a null opt, it means I didn't find anything. I need to go to the next 32 bytes. This is the code. Otherwise, okay, I found something. I need to go to the position where I found it. This is pretty tricky, so I suggest to have a look at it. And if you want to ask me a question about this code, I'm happy to answer. So if we take the find, implement it like we just discussed, and we're going to compare it against the standard find if, what will happen? So I specifically use standard find if because when I pass a predicate to standard find if, standard library cannot do anything smart. It has to do one by one because it doesn't know what your predicate contains. Right. And so in this case, what we just wrote, right, will be about 20 times faster than standard find if, which is pretty good. However, if we stop cheating the standard library from all the information we have and actually call toFind will be another twice as fast. How is that possible? This is actually the same problem we just talked about. Like this is the same difference that I showed you between standard memchar, standard mismatch, and memcmp, why an apple were faster. All of that is due to unrolling. Unrolling is a bit of a difficult to understand. Like not a lot of people know unrolling quite well, so let's talk about it. All right. So this is our most basic loop, right? You have first not equal last, last plus first. Cool. Well, we can unroll. What do we mean? We can copy it twice, right? So when we copy it twice, what happens? Well, we removed one jump, right? This is a jump. Now, oh, sorry, we jump every other iteration. Okay. Doesn't seem like much. There is a little bit of optimization going on in this loop thing because compiler can remove a little bit of instructions. So we removed a few instructions. That's all we did, right? Now what we can do, let's say, okay, we can pre-compute the boundary until which we can get by a few elements and then go something like this. While it's less than tails, go per +2, right? And there's a little bit of a tail computations. There is a bit of it in the end, which are both annoying, and can be noticeable overhead on really small loops. But generally speaking, this is good. And what we did again, we removed more instructions from the loop. And finally, sometimes what we can do is we can merge those two. We can like process two elements faster than we could process just one element or two elements separately together. Right? And in fact, find is exactly this case. We can process multiple registers faster than we could check just one. Let's have a look how. So we have 4 registers. On my machine, a register is 32 bytes. So this is 128 bytes that we're going to try to check together for the needle we're looking for. Step 1, we're going to compare all of them against the needle. Step 2, we're going to OR, like this and this is this. OR again. And finally, only in the end, we do some reduction to compute, did we find any matches at all? Right. This is substantially less instructions than just doing, check one and then go to any. Much less instruction. So, and this is, if we do this, we will get performance that is, again, almost as good as standard find, almost as good as standard find, which calls memchar. But this is what they're doing. This is the reason. And in fact, on macOS, so standard find on macOS is not yet using memchar. As I mentioned, there's some recent improvements. But standard memchars that they have is not unrolled. So if find is actually beating macOS memchar by about a factor of 1.5, right? Something like that. Next. Couple of notes on unrolling. So as I mentioned, the fundamental idea of unrolling is to do less instructions. However, like, do you need to do less instructions? Your computer is so super parallel. Like, it can do so many things in as a simultaneously. It can compute so many instructions simultaneously. You have out of order machines, all that stuff. Do you care about less instructions? Here's how you know. You run pair of stat. So pair of stat, Linux pair of is a Linux profiler. Like, you run pair of stat on your micro benchmark, and one of the numbers it will spit at you is called instructions per cycle. Aha. So now basically the question is, do you need to know how many instructions per cycle your computer can do? And then, so my computer can do 4 instructions per cycle, right? And if I see a number in that pair of stat tool, I see like 3.7. It means that I am utilizing my computer to the fullest. Like, as much parallelism, as much out of order stuff it could do, it does. So I need to reduce the number of instructions to be faster. If it's at like 1 or 2, it means that my computer can totally do more instructions, right? However, like, it means that I have something preventing executing more instructions parallel. Like, it can be some dependencies or whatever. Basically, if you look at search, if you look at find like this, you will see that pair of stat shows you like 3 point, like full CPU utilization, no problem, whatever you write. So number of instructions is very good. Finally, I'm gonna mention Duff's device, because if you go online or whatever, like the classical thinking about unrolling is through the Duff's device. Duff's device is weird. So if you don't know what Duff's device is, it's okay. I'm explaining for people who do. You can Google. It's a cute C trick. Well, somebody likes Duff's device. Unfortunately, doesn't work in practice. It's just not really in anything I tried. Specific, more technical reason is it messes with the Leo instructions, and so it completely defeats the purpose of the thing. Anyways, all right. So let's talk about search. So coming back to search, we want to. So remember search. What we had is we had like find plus equal, right? And find plus equal was really well unless there are false positives. So we want kind of like find plus equal, but we want like better behavior when we have false positives. So what can it be? General purpose thing is called a Robin-Karp algorithm. So the idea of a Robin-Karp algorithm, what you do is you hash your needle, right? And then when you check a string, you check the hash. If the hash matches, you validate the whole string matching. In our case, imagine when we did find plus equals, this effective of which is just our hash was just the first character of the string. So let's use a beta hash. Wojciech Müller in his blog, 0x80 blog, suggests to use first and last character of the string. And what I really like about this is this hash works even for one character string, just the first and last character match. So this is the one I went with. Ash Vardanian in his library Stringzilla, he selects 3 characters, and he's really smart about it because he spends, like, he did some statistics and understanding why those 3 characters would be good. And finally, if you look at str, what it does, it uses first 2 characters. well, they kind of don't have a choice because it's str, it's C strings. So you like going to anything past the second character would be an iteration or whatever. Okay. So we're going to try to do this. We're going to try to use first and last character. Let's first understand how it kind of looks theoretically. So imagine this is our haystack. This is our needle. We have to keep track of 2 pointers, like fronts and backs. This is all potential fronts and this is all potential backs. What we're going to do is we're going to, so the difference between them is like needle length -1. Well, right. Then what we're going to do, we're going to load 32 bytes from each one of those. And like we're going to compare against the first character in the needle and against the last character in the needle, right? So, and imagine we've got some picture like that. Now we're going to end them together because you need both first character and the last character to match. And this will give you this picture. So you only get one position and we test the position. We test the position by doing front plus first two in this, whatever, plus offset here. Okay. So let's have a look at the code now. So this is sort of, it will work if you take this code. So we, as I mentioned, we have 2 pointers, front and back. And we have our needle. So needle and needle size, whatever. Again, we have a register. And then we're going to load the fronts, load back. And now we need to check both fronts and back match. This is what we do. Fronts equals the first character, backs equals the last character. That together, all the potential matches. And what we do is we're going to go and we're going to call this function to iterate selected through the potential, right? Because here we need to not just go on the first match, we need to go through all of them. This is why iterate selected. And for each potential offset, we're going to check the needle. So we're going to do the full check. And here I'm just going to call memcmp to do the full check. And if we found a match, we're going to break and we're going to record the answer somewhere. I will let you have a look at this. This is pretty tough. I appreciate that. So if something, if that makes sense, if you want to ask something, it's cool. We're going to improve on this code in a second. But before we do that, I want to show you some code from Stringzilla. Because so I'm using the Eve library, but I want to show you how people do this without the Eve library. So just they compile, they include the intrinsic header, and off they go. And I want to show you that I'm showing exactly the same code, just like written in a nicer way. So as I mentioned, Stringzilla, they check 3 registers. We only check 2. So this is them loading 3 registers. So they go by 32 bytes. This is what we're doing. We're going by 32 bytes, right? They load 3 registers. Then what we do is they check first register against the first needle, second register against the second character, third, and then they end them all together. This is this code. Well, almost. It's this code. And finally, what they do is through all of the matches, they iterate and they call, well, they call CZ equal, we call memcmp, right? This code is exactly this code. So hopefully I convince you that I am indeed showing the real thing code. Okay. There are a couple of improvements we can do. One is we can unroll the pre-check. Right. Checking for 2 characters is still very cheap, and it's small number of instructions, and it makes sense to unroll it. Second thing we should do is we should inline the needle validation. We right now in the code we wrote, we call memcpi, memcmp. That's not great. We want to do that inline. So let's do it. This is a scheme we used for find, right? We loaded 4 registers and we kind of compared all of them and we combined them and we did any. I'm not going to ask you to type it, but I'm going to give you a second for think about why I don't like it for search. So the problem that I have with this scheme for unrolling pre-checks for search is this any. Like we, at the end of this, we'll just know, did we have a match on the first and last character? We wouldn't know where. In case of find, it doesn't matter because as soon as we find, yes, one time we'll have to redo some work, but that's it. But in case of search, false positives can be a lot, and we care about the performances of false positives. So I do not do this. However, if you look at the libc and glibc, they use 16 byte registers, and they use exactly this scheme. So they check 64 bytes together. To be fair to them, they have a few versions of the loops that are really clever about it, but there is definitely a version of this loop that just checks 4 registers together. Okay. So the second thing is needle validation, inlining needle validation. All right. So imagine we had a short needle. Well, we could do as we discussed with the tail of memcp. We could, select between which two sides this is going to be, and then two overlapping registers and compare them. That's cool. However, there's a function. It's annoying. Let's do something else instead. Let's prepare ourselves a register. We're going to prepare ourselves a register. The beginning of this is going to be our needle, right? And the end of it will going to be some garbage. It's okay. Then the whole needle validation, yes, setting this up will take a second, right? Well, obviously not a second, but some moment, right? But then you can just compare this, and the check is going to be super cheap because you just compare, add a mask, and that's it. Now let's talk about the long needle. So in the long needle, what we can do? We can, again, pre-compute. We're going to take the first register of the needle. And then from the second one, we're gonna just do a little bit of an offset, like you see they're overlapping here, and we're gonna just have so that we can check the tail of the needle by 32 by the whole register. Right. So this is gonna be very cheap. Well, first of all, we're gonna just check this first register, and it's gonna be nice. And then we okay, so we have to loop, but it's again fairly cheap, very cheap. And one interesting thing about this is actually this check and this check for the beginning of the loops are exactly the same. They are, if you're willing to accept a mask when comparing, they're gonna be the same. So then you don't need to actually, in actual code, to split between short and long needle. And with this, we're going to do the numbers. Okay. So this is the first number, is 1,000 bytes. str is slightly faster than what we wrote. 1,000 bytes, the first character is never encountered, right? We just blast through. str is slightly better. This is because of tail handling. They are doing better tail handling than I am. I maybe should fix it. It's pretty difficult. On macOS, str is not implemented very well, so this number is not terribly meaningful. We beat standard str by a factor of 10. Now, this is the same benchmark, but I just, instead of 1,000 bytes, I'm going to check 10,000 bytes. And we can see that on 10,000 bytes, we are substantially faster than str. This is because we use 32-byte registers, and they only use 16-byte registers, right? And yes, they do slightly better tails, but on 10,000 bytes, it stopped mattering. On Apple, again, this is not a very interesting benchmark. It's a 10x win, easy. Now let's look at false positives. Remarkably, on x86, on 1,000 bytes, the false positives are exactly this, practically indistinguishable from the scalar code, right? So, and the scalar code, there's a standard search, right, which is just a normally written loop, is the best case you can have for this, for first character failing, first character falling through, second character kind of like it's the best you can write. So this is very good. On Apple, it's not as good. Again, str is not an interesting benchmark here, but this is about 1.5 times slower, which is okay. Like, you know, we eat something for constant false positives, but it's not critical, hopefully. However, like comparing against str is not that interesting. Whenever I say Apple, do I mean Apple Clank? No, I mean Apple M1. This is not Apple Clank. They are, it's Apple libc. Clank has nothing to do with it. It's a libc that is shipping with your whatever. No. Yeah. Now let's have a look at. So okay, comparing against str is not that interesting because you know str is okay, not on Apple, but it's okay. Like, however, it's interesting to compare against standard search, where if you could use str, you probably should, right? But not everything is now terminated or whatever. You cannot just use that. So let's look at comparing against scalar code. So for chars, we're about 15 times faster compared to scalar code on 10,000 bytes. For shorts, we're about 8 times faster, more than 8 on x86. And for ints, we are about 4 times faster. On Apple M2, sure, so Apple Clank as well. This is going to be, compared to scalar code, we're about 10 times faster. Well, 9 for chars, 4 for shorts, and about 3 for ints. Huge thanks to Joel Falco, who reviewed all of my pull requests, and Ilya Albrecht to help me profile some stuff, and all the amazing people who publish their results online so that I can use it. As you can see, I did not have to invent that much. Mostly, I just looked at what other people do, and I tried to do my version of that, just generic and stuff. So some links. There's a library on GitHub at GitHub, so Falco Eve. There's the slides. Again, the slides are in the chat. I did a couple of similar talks. So I did my first SIMD, which talks about just a bunch of SIMD algorithms. There's advanced SIMD algorithms and pictures. I suggest the meeting C++ version that also talks a bunch of different SIMD algorithms. There's a talk about the library that me and Joel did called SIMD in C++ 20 epoch for new era. And finally, if you want to talk to SIMD with people, cpplang's SIMD channel is pretty good for that. And with this, I'm okay taking questions. More questions if you have any.